Alright, AP Chem, this is your video lecture for Chapter 6, Section 2, talking about enthalpy and calorimetry. Okay. First, we need to talk about changes in enthalpy. Okay, enthalpy is a state function, or the change in enthalpy is a state function. We defined state function in the last section. What we want to point out here is that change in enthalpy, which is represented by delta H, is equal to Q, which is heat, at constant pressure. So as long as pressure is constant, it's unchanging, the change in enthalpy equals the heat. Okay, we're talking about the same magnitude, the same numbers here. And we're talking about change in enthalpy is the enthalpy of the products minus the enthalpy of the reactants. Okay, so we're talking about the enthalpy of products, enthalpy of the reactants, finding the change there is what we're doing. And so, let's start off with the idea of putting that into practice. So, consider the combustion of propane. That's a 3-carbon molecule combusting with oxygen. And we have a delta H, okay, a change in enthalpy of negative 2,221 kilojoules. So if we assume that all of the heat, all of that delta H comes from the combustion of propane, we want to calculate the change in enthalpy in which 5.00 grams of propane is burned. Okay, so 5.00 grams. Now, again, we're going to use some stoichiometry here. You have 5 grams of propane. You're going to convert that into number of moles, use the mole ratio, and use that value there. Let's see. So I'll pause the video and see if you can come up with the correct answer. We're looking at negative 252 kilojoules. Now, these types of problems will be the types of problems that we work on in class. But if you want an explanation of how to do this right now, this very problem is a problem that you can Google and come up with an example work through pretty easily. So calorimetry. Okay, like calorie, okay, a unit of heat. Calorimetry, we're measuring heat here. Calorimetry is the science of measuring heat. A couple of things we need to be aware of, some new terms. We have specific heat capacity, sometimes just referred to as specific heat, but specific heat capacity is the energy required to raise the temperature of 1 gram of a substance, just 1 gram of it, by 1 degree Celsius. Okay, not Kelvin, not Fahrenheit, but 1 degree Celsius. Similarly, we have molar heat capacity, also sometimes simply referred to as molar heat. It's the energy required to raise the temperature of 1 mole of a substance by 1 degree Celsius. So let's try to keep those terms straight as we move forward. Now, if two reactants at the same temperature are mixed and the resulting solution gets warmer, this means that the reaction taking place is exothermic because, like we learned last section, energy is being released. That's why it feels hot. That's why it feels warmer. And an endothermic reaction would cool the solution. Okay, so if two reactants, again, starting at the same temperature are mixed and the resulting solution gets cooler, that means it's an endothermic reaction because it's absorbing heat from its surroundings to drive the reaction. So here we have a very simple calorimeter. It's a coffee cup calorimeter, and it's actually surprisingly simple. You take 2 styrofoam cups, and you put them inside of one another. And so what you've done is you've created an actually pretty darn effective insulator here. And so what we have is the 2 styrofoam cups. We cover it. Okay, we cover it with that good styrofoam insulator. We have a thermometer, so we can measure the heat. Okay, we can measure the amount of energy that's in the system, and then we have something that's going to allow the solution to be stirred, make sure there's a good mixture. So in this section, one of the more common The equations that you're going to use is an equation for energy released, okay, or the amount of heat. Your book uses the terms S to represent specific heat capacity. M, lowercase m, equals a mass of the solution in grams. And then delta T represents a change in temperature in degrees Celsius. I just want to point out that in other courses, other textbooks will use Q to represent this energy release, this heat. Okay, it'll use Q. And it'll also use a capital C to represent the heat capacity, the specific heat capacity of that particular substance. So just heads up, when you go to find some extra help online somewhere, you may see this represented, this very exact same equation represented as Q equals MC delta T. And commonly it will be referred to as a MCAT, MC delta T. But what this equation is saying is that the amount of heat that is being released, or the amount of heat that goes in to a system, depends on the specific heat capacity of that substance. Okay, how much energy it actually takes to raise 1 gram of that substance 1 degree Celsius. We have to take into account how much of the stuff is there, so the mass, and then we have to take into account the change in temperature, how much we actually do change the temperature of one or of the particular mass in question. So using that equation, we have a concept check here, check for understanding. A 100.0 gram sample of water at 90 degrees Celsius is added to a 100.0 gram sample of water at 10 degrees Celsius. And I want you to use the equation that I mentioned last slide to solve for this this problem. Now, you can just look at these numbers and guesstimate, but I'm going to give you another check for understanding right after this, in which you will not. Okay, you will not be able to do that. You need to calculate a specific number. And so what I want you to do is I want you to remember, back to last section, the amount of heat that is gained has to equal the amount of heat that is lost. All right? They have to be the same, because in the universe, no energy can be created or destroyed. That amount of energy is constant. So if we're mixing two samples of water together and they have different temperatures, they will come to an equilibrium, and the cooler water will gain heat from the hotter water, the warmer water. And so what you're going to do, for this particular check for understanding is you're going to use that S times M times delta T, and you're actually going to set up a side-by-side system. You're going to have SM delta T equals SM delta T. Now, one side of the equation will be the 100 gram sample of water that is at 90 degrees Celsius, and the other side of the equation will be the sample of water that is at 10 degrees Celsius. All right, so that's your hint. Again, if you're struggling to get started on this, be sure to check your book, and a simple Google search will help you on this. Go ahead and pause the video, come up with a response. And the final temperature is going to be 50 degrees Celsius. Now, like I promised, I've taken a very similar situation, but I've changed one of the terms. We have a 100.0 gram sample of water at 90 degrees Celsius, but we're adding it to 500 grams of water at 10 degrees Celsius. Okay, so the final temperature of the water will be, go ahead and pause the video. It'll be between 10 and 50 degrees Celsius, because there is more of the cooler water, so the final temperature will be cooler. But what I want you to do now is calculate the final temperature of the water, the actual value. So go ahead and pause the video and see if you can generate an answer with here. And I hope you came up with 23 degrees Celsius. Again, if you're not understanding how to set up this equation quite yet, a simple Google search will help you. This question is actually online quite a bit. And even if you decide not to do that, be sure to attempt these problems the homework assignment that I've given you so far and be ready to go to work next class period. All right, you're going to use the same setup, the same S times M times delta T setup here for this check for understanding. You have a styrofoam cup with 50 grams of water at 10 degrees Celsius. You add 50 grams, a 50 gram iron ball, which is at 90 degrees Celsius, to the water. Now, the specific heat capacity for water is 4.18 joules per Celsius gram, and the specific heat for iron is 0.45 joules per Celsius gram. So, the final temperature of the water is, go ahead and pause the video. It's going to be between 10 degrees Celsius and 50 degrees Celsius. Now, I want to point out that the specific heat for water is about 10 times greater than the specific heat for iron. So what that means in real life is that in order to raise the temperature of 1 gram of water 1 degree Celsius, it takes 10 times the amount of energy to accomplish that for water as it does for iron. So that means iron can change temperature very, very quickly, whereas it takes water a lot longer, a lot more energy to change temperature. You can think of it if you were to put an iron bar over a flame. That iron bar is going to heat up very fast. But if you put a pot of water on the stove to heat up so you can cook your spaghetti noodles, you're going to be waiting about 20 minutes. Okay, that water takes a lot more energy to heat up. Now, I want you to calculate the final temperature of the water. Go ahead and pause the video so you can come up with an answer to this. Hope you came up with 18 degrees Celsius. Alright, and that is all we have for the video lecture for section 2. Again, if you need any quick help, you can send me an email. You can Google search some of the issues. Be sure that you're reading the book, attempting these problems, so that you have specific questions to ask me during next class period. All right, I'll see you next period.